Good morning. I'm Mandy Clark with the City of Arlington, and we're going to be talking this morning, and I recognize that lunchtime is on its way, so we'll do our best to end on time. I'm going to be giving a brief history and overview of the project, and then I'm going to turn it over to Jerry Sanders, and he's going to give the more detailed design specifics and construction specifics. So this project was located on a tributary to the Trinity River in northeast Arlington near the intersection of Green Oaks and 360. A little bit closer view of it. It was a residential area up to the north. There was an apartment complex to the south. The creek ran through here in the purple. There was a 27-inch sanitary sewer line here. So quite a large, this mouse isn't working too great, but you can see it there. And we became concerned because this manhole, we were seeing it getting closer and closer to the banks. And this creek had a history of erosion, and about 3 years ago, our water utilities department had come in and lined this bend with gabions. And so we were concerned that this was going to become exposed, so we needed to get in there fairly quickly and get something done and get that stabilized. In addition, there was a storm drain outfall here that had lost a head wall already, and joints, the joints were falling into the creek at a fairly alarming rate. So we needed to get in there and get something done. So our traditional methods are to just line things with gabions or concrete, and we wanted to try something a little, we don't do concrete lining anymore. We wanted to do something a little less, a little bit more environmentally friendly. So we wanted to use a bioengineering method to give us some more flexible transitions to the creek, because it's a fairly long natural creek, and we needed something that would be flexible upstream and downstream and tie in. We also knew that we would have difficulties with the core if we came in and lined it with gabions or concrete. And then we did want something prettier. It was a residential area, so we wanted to give people something nice to look at. So these are actual pictures from the project, so I think it looks pretty nice. A little bit of the history, the timeline. We chose a design build delivery method, which is something that we had never done before on a traditional public works project. The design build delivery is allowed for public works projects. Arlington gets 2 per year per state law. It varies depending on your city's population, so we use that provision of the state law to do a design build. We did an RFQ and RFP process. The state has very prescribed rules on how you go about doing design build for traditional public works projects. And we went about it that way. Now, because it was something that the city hadn't done before, we had to create a new contract. So there was some time involved at that. But the design build did give us that, we were able to do it quicker than a normal design bid build. And it allowed the contractor to have more flexibility in the field, because there's more working together of the engineering and the construction, and due to this type of construction, it allowed him to make changes quickly and easily. So that was the challenge, or as I look at it, is the opportunity for me to learn from my mistakes. And then we went about it the summer of 2011. We had about getting it approved, and then design happened from September to December of 11, and then in January we started construction, and that is the month that the sewer line became exposed. So we got really lucky. We were very blessed that we were in there and ready to go when that happened. It was about 700 linear feet of channel. Our original contract was a little over $1 million. Our contract is with Sanco. Jerry Sanders, who's going to talk to you here, he was our contractor, and he subbed out the engineering design to JEA Hydrotech, who did the plans and the H&H on the project. We did have one change order, so it ended up being a little bit over 1.1 by the time we were done. I did a cost comparison to gabions, Just pure gabion lining alone would have been about 1.3, and that's without any engineering or appurtenances, fill, mobilization. That was just the lining. So I feel like we got a good deal and a very nice project. So now I'm going to turn it over to Jerry and let him talk about the design and construction.
Okay, we basically moved into the project, and as you can see, as Mandy was outlining, you had these areas of serious erosion along the sides, and basically the sanitary sewer line was exposed, and we had an existing storm sewer that, inlet that was dropped into the channel. The thing that we have to keep in mind is that when we're dealing with creek channels, urban creek channels, is that we're not dealing with a channel that you have a large floodplain or the access to dissipate the energy of the flow over an expanded area. Normally we have flash flood events. This channel normally has anywhere from 6 to 7 inches of water running down the channel, anywhere from 4 to 5 feet in width. One small rain, the channel can change. Immediately it goes to 4 to 5 feet in depth and 22 feet wide. If you have a major rain event, it can drop up to 8 feet in depth in just a flash. And it stays at that for a period of time because the watershed is so large and it's coming off at such a high velocity. So what we're dealing with is high stress on the banks. As you can see by looking at these banks down the channel, you can see that they're highly eroded. Some of the banks are as high as 15 feet, 16 feet in some areas, and the erosion is occurring exponentially, because what happens is as the initial erosion breaks down the structure of the bank and its curvature, its natural geomorphologic structure, then it increases and starts to grow at a more rapid pace. What happens when you have your erosion? Well, you lose a lot of land. You lose the space, the land immediately starts disappearing, and you also lose a lot of infrastructure. You can lose sewer lines. As you can see, the sewer line here is exposed across this bank, and you can see here where this fence comes to a dead end. There used to be a jogging path right out here, and it came across here with this fence. And so we have an immediate loss of property and a lot of potential for damage to utilities, subsurface, as well as along the surface. Not only do we lose that, but we lose the trees, and we increase our maintenance and our care for our channels. As the erosion occurs, the trees are undermined. The trees, through natural procedures, fall into the channels. Now, these trees falling into the channels have taught us a whole lot about how channels run and how the natural state of a channel evolves. But we don't really need that happening in some of our urban channels, because we're already losing the banks, which are a limited area anyway, because we have buildings and properties right up next to us. And so we try to minimize the amount of the trees that we're going to lose. This tree right here, for example, has a 6-foot cut back up underneath it at this time. And a little later in the presentation, we'll look at this tree where we were able to try and save it. By using bioengineering, or biotechnical procedures, what you're doing is you're using a biotechnical is to use vegetation, plant material to stabilize banks. But sometimes the stresses and the speed and the velocities and the volumes of water that you have coming through a channel requires you to enhance that. And so you enhance it with engineered products. And so therefore you get a biotechnical or a bioengineering procedure. When we got into the project, you can see the immediate loss of some of the structure that we had. This was the inlet that Mandy mentioned. This inlet started out right here. It fell off and was pushed down 230 feet down the channel. The inlet's 6 feet tall and 18 feet across. It's not a small piece of concrete. It moved very rapidly down the channel. So you can tell how strong and powerful the water flow is. So how do we deal with these types of activity and maintain them to get stability within the channel? Now, all of us know that there are some situations you're going to have to use hard structures. But over the years, what's happened is we've developed a better knowledge of how channels work, and we've developed a better way of understanding how the flow works in the channel. By using that information, as well as an understanding of new technology, different types of products, structural products that we can use to create soft armor, we can now go into places where you used to not think about going into with a soft armor installation. Some of these products are geogrids. The geogrid, of course, is a reinforcement product to stabilize banks and allow you to have steeper channel banks with a stabilized earth installation. It protects the earth as well as allowing the plant to have something to grab a hold of inside the soil. Weirs. For years we've been playing around with different installations of how to put a structure into a channel so that it would actually help us maintain the banks of the channel. All we had to do was look at how the trees fall into the channel and what happens to them, or see how rocks are falling into the channel, and then to walk the channel and see how it impacts the further down the stream. Once we started doing that, we started realizing that you don't point a weir downstream, you point a weir upstream. So many times we think we're going to direct the water by putting a hard structure and directing it. That's not how water works. Water works in the reverse. If you point upstream, you can direct the water, and you can direct it by the heights of your installation. So weirs become a very integral part of directing water flow throughout a channel so that you can eliminate the direct impact on the side walls of the channel as well as along the bottom to stop V-cutting. Now, I'm going to talk only about one type of weir in this presentation, but there are numerous weirs that you encounter. You can have a Benway weir, which is what we'll discuss because I want to talk about direction. You can also have sandbarbs, which basically are for sedimentation and building up of the banks. And you can have J-weirs, which are to create the meander in the channel. The meander has to be there so that the flow will stay clean, continue the bed load carry, and at the same time, cool the water. Keep the water cool so that the fish and other animals can inhabit it. Of course, that includes snakes, and I know that kind of drives a lot of people crazy. The other thing is drop structures. Drop structures are set up to maintain and keep us from having continued head cut or to keep us from having grade changes within our channel. Now, a drop structure increases a tremendous amount of turbulence, and so you have to also, in your drop structure, apply or put in additional structures to dissipate that turbulence or that large amount of activity that's going to occur. So let's look at geogrid embankments. I'm sure most of you are very familiar with the installation of reinforced earth. What we use there is we use a geogrid installed in layers of compacted earth, but there's more to a reinforced earth structure than just the compaction of a geogrid or an engineered product into it. A structure like this requires that you drain the back side of it because you're working along a creek channel. The reason creek channels form is because water is migrating toward it along subsurface and surface channels. So you have to be aware of that and address that. You also have to address, do you have any room for benching? Numerous times we're caught into a vertical channel where we have no room for benching, or we have a situation like this with the storm sewer sitting right here. We can't bench back in past that, yet we have to maintain some stability in this new block of earth that we're going to build. So we use earth anchoring. We can anchor and pin the earth together. Anchors can be taken and driven back into the earth, pinning the blocks of earth together. Here you see the construction of the reinforced earth going up. The reinforced earth structure basically stabilizes the structure. The drainage drains it from the back side. The anchoring pins it together. But what protects the surface? What takes care of it? Grass sods and other materials will go 3 to 4 feet per second of flow. If they stay in a saturated condition, of course, they're going to deteriorate much quicker. So basically, what we're looking for is something where we can gain additional flow capacity. So we go to different types of erosion mats. Now, there are a number of types of mats that you can use. And today we have mats that will take us up to as high as 20 feet per second. And we can get into a saturated soil area, and we can stay in there to 12 to 14 feet per second with saturation over a period of time. So what we try to do is we try to use the plant, maximize its ability. And in this scenario, what I wanted to do was to maximize not only the ability of the plant, but to increase the tensile strength of the bank so that I spread my mat over the top of my plant material and then anchored it into the surface. This allowed me to have root structure for strength and stem structure. It also gave me the strength of the mat itself to help me with the shear stresses that were going to be placed on the bank as the flow came through. And then it was anchored in. And we'll get into a little more detail of how that construction goes about in a moment. Yes? Oh, okay. I get carried away. I start moving toward the crowd. Did you notice that? Anyway, okay, let's go to Benway weirs. What is a Benway weir? As I mentioned, a Benway weir assists us in directioning of the water. We can install the weir in an upstream manner. Oops. It faces upstream, and we stick it out into the channel. Depending on the width of the channel determines the length of the weir. You don't want to be over a third out through the channel. If you get out past a third of the channel, then you're going to start obstructing the flow, and if you obstruct the flow, you're going to erode the opposite bank. So the weir normally goes in usually from a 15 to a 45, they say in the manual, 35-degree angle. I've gone out as far as 45 degrees because many of the meanders have a longer reach. And you have to keep in mind, you're not dealing with something that's drawn on a piece of paper. You're dealing with something that's real in the field. And so these decisions have to be made in the field at the time of installation. So as you're setting the weir in, you're also going to have to look at different aspects such as height, angle, the disbursement, how far apart, those type of applications. So the weir directs the water to the center of the channel. And this right here, you can see that we had a series of weirs coming down where the curve came out and hit the sewer line. Downstream, you have another series of weirs here. Over here, these are Benway weirs. Inside here, these are barbs. I'm wanting sediment all around here, and I'm wanting to direct this flow to the center of the channel in those other areas. This is basically how the weirs work in action. If you look at the weirs, the photo is kind of, I can't hardly see it, it's a little bit too light. But it dissipates right here in these corners as down the weir. You can see as the flow of the water comes by, this is all stable and very, very mild or gentle, laminar flow in there. And as it comes around the weir, it moves toward the middle of the channel. And that's what we're trying to get to. If we look at it in a flowing pattern, you can see that as the water hits, if we could see it a little better, it turns the water backwards up across the back side. The water goes in reverse. Let's look right here. As it comes down, you can see that the water goes in reverse. Water will actually hit the weir, go past the weir, and on the inside, it will come back and eddy behind it. And as it gets deeper, it will actually come back over the top of the weir and come up the channel. Some of the photos that we have, which I don't have in this presentation, they show the grass sod there, the grass that has grown out there is actually the water has come down the channel after a major event, and you can see the grass laying upstream. It's going upstream. At each one of the weirs, it's turned and going the other direction. The reason is because the eddy is formed. Now, the higher that we have the weir in the back, the farther up or the deeper the water I can turn and force to go back up the channel and give me a laminar flow right there next to the bank. So all of my erosion would occur out in the center of the channel. And that's where I want it to move to. This is another one that shows basically how the water comes down the channel. This is coming around the corner, and here's the weir right here. This one's set at a 15 degree. That's a 1 foot top and a 2 foot back. You can see immediately, see how it's coming back? See that circle? It's forming right there. It's forcing this water toward the center of the channel. Now the movement of the water toward the center of the channel is totally dictated by the elevation and the angle of that weir. Drop structure.
Are you getting supercritical flow in that stream?
I'm sorry?
Are you getting supercritical flow in that stream?
Not all the time. No.
But in high flow rate?
The high flow rate, the flow rate that we projected for is 8 feet, and the highest that we've seen at this time is 6. And we've had some major flow patterns.
What would you say the highest rate was?
8 feet deep.
18 feet per second?
Oh, no, they say 12 feet per second is what, 12 feet per second is what they, I'm old school, and so when I was out there during after a major rain event, I used the old tennis ball, dropped it in the water, and measured my time down through there to try and calculate. what I thought that the flow was going to be, and it was a little higher to me. So that's why I opted to move with a little bit more, I guess, stronger erosion mat. And I used the grass under the mat so that I could increase the ability of the grass to absorb the energy. The weirs are at drop structures. There's two different types of drop structures used in this installation. One of them is a drop structure which is called a hard point. What I did is you back up the stream to the end of the cut where, for example, it was head cutting backwards up the stream. At this point, we used the little hard point here. This hard point, as you can see, is very shallow here, but that's actually 7 feet deep. It goes down. The hole here was 7 feet below grade of this sandstone ledge. So I chose this as my hard point. In the I guess approximately 6 months of time between the time we actually got the contract and we actually started, this point had moved back 7 feet back upstream. And so I had to adjust everything in the stream to that hard point. So we moved the hard point back up and put it in. Now what the hard point does is it protects this from head cut, but the thing it also does is I put a plunge pool at the base of it. The plunge pool is there to dissipate the energy. Now if you've ever done any river rafting, for example, I'm a big river rafter, you notice that as you go down the stream, when it hits the deeper holes, the water turns and comes up at you, back upstream. That's exactly what's occurring here. The water's turning and it's coming back upstream. This takes the energy out of the water so that it slows it down and it drops its load, and basically you're able to see this happen in the water itself coming back at you. Another drop structure, and you can see this one basically is an A-frame drop structure, and we did this strictly because of Arlington to make this A, but actually no, that's not why we did it. The A-frame drop structure is built because each side is a semblance of a Benway weir. If you look here, you'll see that one is tighter, one is more open. What I'm looking to get here is looking to have the water as it comes down and hits this bend, I'm wanting to turn it immediately back into this channel, into this drop structure, so all my turbulence is here. I have two plunge pools here, and then I have a third one right here at the bottom of the channel. On this side, I'm wanting it to drop sediment, and I'm wanting to create a bar here. A plant bar is what it would end up being. And basically, as the water comes over, you can see that it will move toward the center because of the weir installation. The Benway weirs here are moving this water. This is moving this water this direction. This weir is also moving it that direction, but it allows it to drop sediment on the back side. Now, this thing goes totally under, probably 2 or 3 feet beneath the water in just a small rainfall. Doesn't take a whole lot. Up there's the A right there. Okay. Now you can see there that it outlines where the plunge pools are, but the plunge pools are here and here and here. They do a great job of dissipating the energy as it comes over. As the water flows over, this is a minor rain. I just happened to stumble out there after the rain. It takes about 5 minutes and bam, it's there. And it starts coming over, and as you can see, as we go down the channel, you see where the Benway weirs are. They're going to direct the water here. This is the side panel. So as it goes a little further down it'll show you how the water is directed even more toward the center.
Are you using gabion boxes to build those Benway?
No, I'm using stone, natural stone, to construct all of this.
You're not in a wire box?
Nope, these are solid blocks. If you look here, you can see how the gabion. See now, watch this foam. You see the foam forming here? It's going toward the center. As it go past this, that foam line right there, that's where I want my turbulent water. I want it all coming to the center. See how gentle it is up here? I want all of it here. This weir is directing it. There's another weir downstream from there. Those weirs direct that flow to the center and keep all the pressure off the side banks. So my erosion bank and also my ground cover, my grass covers or different types of plant materials that you can use will stabilize and hold that bank. And rather than deteriorating or being damaged, they'll actually repair themselves because the ground covers will regrow through if there is some damage for them. Construction and installation. So let's look at the construction of the area right there next to the utility. How much time do I have?
About 7 minutes.
7 minutes. We're going to have to hook them. When you construct it and you're in this situation, of course, the first thing that we had to do was we had a manhole right here that was exposed. There was the sewer line. So to secure the bank, I used earth anchors. And the earth anchors, you can see, are driven in these patterns here. These anchors go 15 feet back into the native earth, and then they are plated at the back side. Down here, I've located the seams in the bank, and I've put in the composite drain materials. All of you are familiar with composite drains. They're manufactured drain material. I put those in to intercept the water and take it out to the bottom of the channel. Once we can start construction of the layering of the geogrid materials, the anchors are extended to the face of the bank. Come over here, you can see there's the larger anchors there, which are the anchors that actually hold the bank against the other bank, pin it together. Over a period of years, that seam will heal itself. But it is a seam right now. That's why benching is so important. But you can't do that in this scenario, so we use the anchors to buy us that time for that healing process. As you can see here, right there, the grass is being installed onto the bank, and then of course the mat being installed right over the top of it. Within, another amazing thing is that the mat is black, and so the sunlight hits the mat. So if you're working in dead of summer, it's going to be hot. You got to keep it damp so you don't burn your grass up before the grass gets outside of the mat. If you're working in the winter, the heat heats the ground, the grass comes out earlier, so you have green grass in the middle of the winter because it's heated up, and it keeps it coming out. The weir, here you can see before the installation, you can see the small tree there on the bank, and then we put this installation in. This is what the bank looked like, and the tree was hanging off, and then of course there was a pipe here, an outlet pipe. We came in, we backfilled, started our compaction and our backfill. In this area I was able to use a lightweight material for my erosion mat because this is on the inside of the curve, and I was able to then put my grass down, pin it in with the earth anchors here, and of course pins, sod pins, and allow the grass to start growing through. Within about 2 months, you can't see any of the plates, you can't see anything that resembles that installation. Here we are again doing the same thing. This is the tree that we had looked at, had the 6-foot opening underneath it. Right here it is. You can see we're building up to it right here. We hammered in our anchors underneath. I told Mandy I'm kind of like a little old maid. If I see a tree and I know I can save it, I go underneath and I trim the roots just like you would if you were going to harvest a tree and ball and burlap it. Okay, so that roots are hanging in the air. If you bury the roots that have been hanging in the air, they'll die because they've been hanging in the air. So what I do is I go in and I trim those off and I treat them. I usually use Super Thrive or some type of stimulant to treat them, and then I put the dirt right back in on them and pack them back in, and then put my anchors on the outside and hold everything together in that manner. And there's that tree right there. This year, that tree is doing great. I mean, well, I've been back out to that site, and the tree is just totally full. The leaves look great on it. In fact, they're bigger than they were the year before, showing that the tree is pretty healthy little installation. All right, this is the end instruction. This is where your Gabions come into play. I'm not a big Gabion person, but I know they have an application, and I use them where they have to be used. And in this instance, we had an inlet coming in, and it was dropping to the base of the channel. The channel used to be about 5 feet higher up. It had head cut down. That's why the head wall was gone. That's why as you can see here, the tube or the drain line itself had fallen off. What we did is we constructed a plunge pool area here. It was a total of 6 feet from here to the bottom of the tube. I took the old tube, cut it off so that it fit nicely to the angle of my bank, because the worst thing you can do is stick a hard structure out there that gets hammered every time it rains. So I put it out so that it was a smooth structure, and then I allowed the water to come out and go into the plunge pool. The plunge pool helps you, maintains keeping the water cool. This pool is the same elevation as the channel when we finish. This is before and after photos of the installation. You can see that the trees are, this tree here was salvaged off the bank there. This is where the storm sewer, or the sewer line was exposed. I used a variety of different types of materials, plants. The plants that you use have to be selected based upon the soils that you have. There's a before and after. This is the section of channel I use the lightweight material in. You can see all those plates are gone. There's that tree. There again is the sewer line, and you can see how far it is. It's now about 8 to 10 feet from here back. Right there it was exposed next to us. There's looking back upstream as the grass covered. Now the anchors are gone, the mats are gone, everything is hidden, it's underneath the grass. The thing is that as this gets older, unless you maintained it, let's say you wanted to go out there and mow it and maintain it. I have a number of golf courses that I've done that they mow it and maintain it. It's absolutely beautiful always. And the sod, the silt that comes in over the mat, over the years, you'd think that it would never bury the mat. The mat would just stay right on top, you'd think. But what happens is I've gone back to one project I did, which I did 12 years ago. They wanted to extend a section of it, take out some walls. So we went in and we were going to tie into our mat, and I had to dig 2 inches down through the silt to get to my mat. It had literally silted in. The banks were growing rather than receding. This shows you the number of the anchoring procedure to save this tree. There's the tree that we were talking about that had the 6-foot undercut. There it is today. That's what the channel looks like now. And of course you can remember what was in it before. If you look closely, you can also see that there's vegetation now growing in the bottom of the channel. I tried to create a small floodplain in the bottom of the channel so that I could put vegetation in that area, and we were able to successfully get gamma and switch to grow in that area, and it gives us some stability along the toe so that we can constantly have it repairing itself over time. All right, and this, let's go back here. This is an installation harvested from the site. These are black willow. I use black willow poles, 4-foot poles. I cut them on site, soaked them in the water, drove them in the ground, left 1 foot exposed, and you can see that they rooted out and they started branching immediately. This is another picture of this is the J-weir installation. You can see the height of the water flow up here coming across. The J-weir is made to establish the meander. This is a row of willows all growing. Ultimately, the willows will come up. The log, which is buried in here, will deteriorate, but the willows will establish a root structure behind it. They'll hold the weir in place, and everything will work. It'll just continue to work around. The willow, except the black willow, I like it because in this scenario, when the water gets up high, it comes across and breaks the branches off, so the willow never grows into a tree. It constantly gets broken off, and broken off, and broken off during high flows.
It's a pretty large stone. Where did you get it?
I had those stones brought in from down near Georgetown, Chico. Yeah, down there, Georgia. It was Georgetown. Chico was the larger limestone rock. The stones were sized according to what we were finding in the channel that were rolling down the channel, and so we sized them. Of course, the engineering organization JE sized everything according to the formulas, and I sized it according to what I found in the channel. That's the way I do it. I evaluate things by going down the channel, seeing what's moving, what's not moving. If you've got a stone there that's not moving, I measure it. This is my stone. And that's the way how big I want that stone to be. And placement of stones, you can see right here, now this has willows growing out of it and everything, which is locking it together. But this is small stone. But if it's placed in there correctly, it'll sit there as long as that plunge pool is there, because it takes the pressure off the stone when the water rolls backwards. It rolls up the hill. Any questions?